All right, thank you everybody for joining. This is our inaugural showcase webinar where we have an outside expert come and present a technical topic for us. So today we're going to be talking about optimizing steam system or steam process heating applications. I am your host. My name is Chase Bean. I'm the Director of Engineering and Business Development for Steam Management. I'm going to be moderating your questions today. So any questions that you have, just put them in the chat, the meeting chat, and I'll point those out to Justin, our speaker, along the way. We also have a few polls that we'll launch during the presentation. So those will pop up on your screen and you can participate in those. And then as always, our PDH certificates are available upon completion of the webinar, and our process for that is just to email me at my email address shown right there, and I will send those out to you upon request. Steam Management provides turnkey retrofit projects with a focus on efficiency improvement in steam systems. These solutions reduce system energy costs, conserve water, and reduce carbon footprint by an average of 10 to 30% for most clients. So the opportunities shown here are common measures that we evaluate and implement for our clients. That's kind of a high-level overview of what we do. If you're interested in having a conversation with us afterwards, feel free to reach out as well. TLV was established in Japan in 1950, and TLV has grown to become a world authority in steam engineering products and services. TLV produces steam traps, condensate recovery pumps, pressure-reducing valves, and other steam-related equipment. TLV has developed a broad range of solutions, including steam traps, valves, and separators, as well as sophisticated system products and software. To date, they have obtained over 4,900 patents and utility models across the world, underlining their commitment to creating new, innovative technologies. Also, TLV has a great library of technical resources on their website, so be sure to check that out as well for a variety of topics pertaining to steam systems. Today, our speaker is Justin McFarland. We are thrilled to have Justin with us today. He is one of TLV's leading experts. He is a consulting and engineering services senior applications engineer and has been with TLV for over 13 years. He's a degreed mechanical engineer, also has his master's in mechanical engineering from UNC. He is an Association of Energy Engineers certified energy manager, an IEP certified professional energy manager, and a U.S. Department of Energy qualified steam system specialist, which I'm jealous of because that program, to my knowledge, no longer exists. So I will never be able to get that one. So I'm a little jealous of him there. He also earned a Top 100 Research Award in 2011, and his project experience includes significant engineering and design work on TLV's power trap system packages to drain towers and other critical process equipment such as reboilers, heat exchangers, and critical process coils, ASME pressure vessels, and custom steam condensate manifolds. He excels in performing on-site steam and condensate system reviews and assisting end users with opportunities to improve energy efficiency, equipment reliability, and process productivity. He has exceptional experience in designing solutions for space-restricted installations, and he does a lot of these types of speaking applications or events for TLV. So this is a great presenter for us, and we're thrilled to have him. So without further ado, I'll turn it over to Justin, and he will tell you about optimizing steam process heating applications.
Okay, so thanks very much for the introduction. Very old picture there, so everybody sees that picture and thinks I'm probably 16 years old. Quite a bit older now. Anyways, I'm going to get on with the presentation. So let me share my screen here. I believe everybody should be able to see my screen. Chase, we good?
Yep, we're good.
All right, fantastic.
See your laser too.
All right, so I was asked to come on today to talk about optimizing steam process heating applications. So this is actually a webinar that TLV put on a couple years ago, back during the time of COVID. So you feel free to get on our website, check it out there. Lots of other useful articles and things I'll point out during this presentations that you can find on our website. So as Chase mentioned, lots of fantastic information and educational topics on our website. So Steam system optimization. This is really what we're talking about today. And from a 3,000 foot elevation view, when we look at a steam plant, plants of all shapes and sizes, they vary, but for the most part, we have steam generation to boiler. We're going to distribute that steam throughout the plant. And the idea here is we want to supply dry steam. That's going to go to various pieces of equipment, tracing, turbines. We want to drain condensate quickly and then return that condensate. Condensate in a steam system, it's not good. They don't mix. Things go boom. So we want to get rid of the condensate and then return that back to the boiler to be an efficient system. So when it comes down to steam system optimization, TLV kind of sees this as a three-phase approach, where looking at condensate discharge locations, and if you're able to have a good, healthy steam trap population, that will, in my experience, and probably anybody else's in TLV's experience, probably fix 90% or more of the problems that our customers see on site. Today we're going to be talking about steam using equipment, so primarily with identifying incidents and bottlenecks, poor operation, and optimizing performance of those equipment assets. So shell and tube heat exchanger. This is a typical type shell and tube heat exchanger I'd see in heavy industry. Sometimes it looks more like a kettle type reboiler like this. There's lots of other different types of process heating steam heat exchangers, whether it's things like a fin tube heater for combustion air, or for HVAC for an air duct for comfort heating. Do something like a tank heater, plate and frame, U-tube, lots and lots of different types of configurations. Point that I'm trying to make here is that no matter what type of process heater you have, or what type of fluid it's heating, the topics that we're talking about today are applicable for all those different types of heaters and all the different types of industries. So just keep that in mind as you're listening. This presentation is probably geared more towards heavy industry, more along the lines of what you would see in a refinery and chemical plant, at least with some of the graphics and some of the pictures. But just keep in mind that everything is 100% applicable to every industry and application that uses steam to heat some sort of process fluid. So what we don't want to see are things like temperature stratification. So it's the channel head of a shell and tube heat exchanger. You can see where it's bright orange at the top, purple down at the bottom. So a big temperature gradient there. Don't want to see things like collars on channel heads that were put in place because of steam leaks at the gaskets. Don't want to see things like corrosion or fouling on the tube bundles. So all those things are problematic. All those things are things that we're going to be talking about as to some of the things that we want to mitigate with our process equipment. And if you do get a chance to go on our website, check out this article written by our former president a while back, but has a bit more information, some detailed information. All of the topics I'm talking about today, get in more detail and see that in a different way. So all the things that we don't want to see. Don't want to see temperature stratification, don't want to see corrosion. There's other things like water hammer. And so with those in mind, I'm going to go through the heat transfer equation. So if anybody is an engineer, maybe you've seen this at some point in your studies. If you're not, I apologize, but I'll go through this quickly and try to explain everything. So heat transfer equation, Q equals U times A times LMTD. So Q is our heat transfer, it's the total heat. U is the heat transfer coefficient. And so that really relates to how easy heat transfers from the hot side, and in case we're talking about here steam, as it passes BTUs through some sort of heat boundary, usually some sort of steel surface, and then into the cold fluid that needs to be heated up. We have the surface area and then the log mean temperature difference. So LMTD, you can kind of simplify that down to, if you can imagine the difference between the process temperature coming in and the process temperature coming out. It's not exactly what it is. It's a little bit more of a complex formula, but it's more or less a way to compare the different temperatures of the hot side and the cold side process streams for this, just to get an accurate temperature difference of everything that's going on. So saw this image earlier, got corrosion, fouling. So if something like that occurs, then probably you're going to have a reduction in your heat transfer coefficient. You're going to get rust buildup or product fouling, caking and building up on the process side of the tubes. All that's going to degrade your U value, degrading your heat transfer coefficient, making it more and more difficult for that process heater to provide BTUs to the process. And then things like flooding, so temperature stratification. So if we're not able to easily drain condensate from the process heater, well then we can view this as effectively removing surface area from the heat exchanger. Now, we're not actually removing surface area, but we're flooding a portion of that with water, and understanding that the amount of BTUs available in steam is much greater than BTUs available in water, as well as the heat transfer rate there. So simplify things, we like to see it as just simply removing area. And so if we change our area, then that also changes our Q value. Generally, what we're trying to accomplish is modulating our LMTD. So this is usually accomplished by something like a steam inlet control valve, where we can modulate pressure. And then assuming we have positive differential pressure, then we can discharge condensate through a trap, and we can easily modulate the Q value based on steam pressure alone. So we saw this image. So things like flooding, it's going to produce inconsistent product quality just because we're going to have temperature control issues. Oftentimes that'll result in water hammer, just due to the presence of hot vapor near a flooded coil, or we've got cold condensate that's backed up. You can get tubes that become broken, ruptured tubes like you see here. Condensate inside the tubes, especially if it's held there for a long period of time and it's allowed to subcool, can cause excess corrosion. So that's going to degrade your U value as well. Things like gasket leaks, that's usually a big visual indicator that something's happening, whether thermal stresses or water hammer or something like that. But gasket leaks should not be occurring. And if you see that, then it's probably something that needs to be investigated. And discharge and degrade, seems like, well, that's not how the system was designed. Why is this happening? Well, typically an operator, they're going to have, an operator's primary job is to make sure that that process heater is operating and the process is being heated to what the spec is. So if something starts to go awry, well then usually an operator is going to say, okay, well the easiest thing for me to do is open up a bypass valve or open up a drain and drain all the condensate to the sewer. A lot of times that fixes the problem, but that's not how the system was designed. And so it's wasteful for, got water loss, got energy loss, but that's another red flag of, hey, something's going wrong here that shouldn't be happening.
Hey, Justin, can you go back one slide just so that list is up and we have our first poll?
Okay.
Just give me 1 second to get that launched. Yeah, so is your facility experiencing any of these systems? Yeah, feel free to get your input on that. And I believe once you put your answer in, it disappears. So yeah, thanks for holding there, Justin. Also, this might be a good time if anybody has any questions they want to put in the chat. We could get those to Justin. Otherwise, I think we can keep on moving while people are filling out the poll.
Okay.
Gasket leaks is the leading symptom people are reporting right now.
Oh, interesting. So I want to briefly get into different types of control systems and what those look like and maybe some of the drawbacks that you would see with that. So first, very simple one, the steam inlet control valve with an outlet steam trap. Pretty simple. So the objective here is to modulate temperature of the process by effectively modulating the steam temperature or the pressure. And you can see here we've got an inlet control valve that is got a controller looking at the process outlet temperature. Got a steam trap here. And as long as we have positive differential pressure, so our inlet pressure here is greater than our outlet here, then we can drain condensate and we can use a steam trap and life is great. As soon as we have a negative differential pressure, meaning that our pressure here is less than the pressure downstream, then what's going to happen is that condensate can't flow. And oftentimes there's a misconception thinking that, hey, I can just put on a bigger steam trap. Well, that's not exactly accurate. There might be some scenarios where that is helpful for sure, but if you have negative differential pressure, it doesn't matter how big of a trap you put on there, it's not going to flow. So inevitably you're going to end up backing up condensate. And then while we're trying to modulate the steam temperature, some of the consequences of this scenario is what we end up with slow degradation in our U value because of corrosion, potential fouling on the process side because we've got hot temperatures here and cold temperatures here. We've got a loss of our our A value. So oftentimes this results in lots of temperature swings to the process. The control valve might be very erratic as well as it tries to accommodate for the losses in BTUs that it's seeing on the process side. So there's a solution to this that we're going to be talking about later, but this is a scenario that we don't want to see. Another type of design is a steam inlet control valve with an outlet level pot. So you could think of this as basically an electronic steam trap. It's really all it is. Got an outlet control valve, got a level pot, but all this is designed to do is look at a level as that bounces up and down or held at a certain level inside a level pot. But still we've got an inlet modulating control valve, and as long as there's positive differential pressure, then this will drain and it will act just like a steam trap and everything's going to be great. But again, as soon as we have negative differential pressure, then there's problems, just like with the last scenario. Next one, a very, very common one I see in heavy industry is outlet control valve. So this is actually designed with the intention to back up condensate inside the process heater. But inevitably, what we often see is that steam is oftentimes blowing through. And I'll explain that here in just a second. So really, really simple system. Instead of a inlet modulating control valve, we have an outlet side modulating control valve. So the reason this is so common is because the upfront cost of this type of system is very, very low. You have instead of having two devices where you have an inlet valve and some sort of drainage device on the outlet side, you have just one valve on the outlet side, which is that valve is probably going to be quite a bit smaller than having an inlet side valve, just due to the differences in specific volume of steam compared to water. So lower upfront cost, but there's some big drawbacks and reliability issues over time. So because this is designed to back up water, well, then we've got a degradation of U, we've got a varying A, so it becomes a very sluggish type response. And over time, as this slowly degrades the heat transfer coefficient, then it's going to basically lower the amount of temperature that can be provided to the process, which will then feed back to our controls and say, hey, control valve, you need to open up more. So that liquid level will drop and drop and drop and drop till eventually there's no liquid level inside the process heater, but it could be past the point of return, in a way saying that there's no more liquid level to be drained. And so what's to stop this control valve from just blowing live steam? So that's a big problem that we see. Keep a lookout for that. I have a hybrid between that and one of the previous systems, acknowledging the risk of that blow through scenario, is having a level override. So the whole objective here is just to have a kind of a fail safe in a way to monitor the liquid level downstream of the process heater, just to make sure that there's some sort of minimum set point. And the very last one, and then the main topic of conversation today, is steam inlet control valve with an outlet condensate pump trap drainage or power trap system. So I'm gonna skip through this. So we're going to talk about that a bit more. I just wanted to show that real quick.
Hey, Justin, if you go back one slide,
Sure.
or two slides, I guess. We got another poll here. I guess you don't need the slide for it, but yeah, you guys participate. Could you use expert consultation regarding your condensate drainage system design? There you go. And again, feel free to put any questions in the chat. We love to get some live feedback while we're doing this, and we'd love to get some more of pick some more of Justin's brain while we got him. So yeah, don't be shy about that. But anyway, yeah, continue on, Justin. Thank you.
All right. Thanks, Chase. So back to using a steam trap. So mention that positive differential pressure is the ideal scenario. So you can see a little chart here that over time, that pressure might modulate on the upstream side versus the downstream side, but we always have a positive differential pressure. And if so, then a steam trap is going to work. But if we have some scenario where at times, or all the time, potentially, we have a negative differential scenario, then a steam trap's not going to work. And then we get periods of flooding, and then all those suboptimal symptoms that we had talked about earlier. So big question in everybody's mind now is, well, why would you have high back pressure? Okay, I understand that that's a bad thing, Justin, but why would anybody have that? Well, could be that just the condensate system pressure itself is high. Doesn't necessarily mean that it was designed that way, but there could be a lot of other issues going on in a plant. Could be that there's leaking steam traps, could be that there's open bypass valves, could be that there's different equipment or units that have been added on over time and trying to put more and more condensate into the condensate return system that's never been upgraded. And over time with all those things, then that can cause a slow or even potentially dramatic increase in condensate return pressure. There's things like high vertical lifts that might not be considered. So rule of thumb, for every 2 feet lift, you have 1 PSI increase in head pressure. And there's frictional losses. So whether that's due to corrosion that's degraded the surface of the pipe walls, or you have very, very small bore piping, or very old piping and things are just starting to degrade a little bit. But frictional losses can certainly increase local back pressure. Now, that probably all makes sense, but low equipment pressure probably is a little bit more unusual to people. So the biggest reason that we see is low process temperatures. Great analogy for this is think about like a hot water system. So if you have a hot water system at your house, it's probably electrical, but let's just say that let's say it's heated by steam. And knowing that, the water temperature when it sets probably not going to be any more than 150 Fahrenheit or so, then I'm just going to guess that, okay, well, the steam temperature that we need in order to get water to 150 is, well, it's got to be more than 150 Fahrenheit. Does it need to be 300 degrees Fahrenheit? Does it need to be 200 degrees Fahrenheit? There's no wrong answer to that. It really all depends on the process heating capabilities. But we find most often that with low process heating temperatures, like something below 200 degrees, that you might only need, near atmospheric saturated conditions. So around 212 or maybe 220 or even 230 Fahrenheit. The corresponding pressures for all that is very, very low. And so once you consider, having to return that condensate even to, let's say, an atmospheric receiver, having to move condensate up 20 feet. So you've got, 20 feet, that equals about 10 PSI back pressure. So that can hinder things to a point where you suddenly, thought, okay, well, I have positive steam pressure, but now you have a negative differential pressure across that drainage device. It's all due to just the fact that there's low process temperature requirements and low BTU requirements. Then there's things like drop in process demands. Could be seasonality. So again, hot water heater, think of like a university or a hotel, let's say, that is heating a pool. Well, in summertime, they probably don't need to heat it up as much just because you've got more heat from the atmosphere to keep it warm. But then in the wintertime or in the fall, then there's more demand for heat. And so they're going to be providing a lot more BTUs during those seasonal times where it's needed. But in the warmer months, then there's going to be a drop in BTU requirements, which will need less pressure and inevitably lead to a negative differential pressure scenario. Got high oversurfacing. This is an interesting one to think about. If I am a heat exchanger manufacturer, I'm going to recognize that, okay, over time, that piece of equipment is going to degrade. Over time, there's going to be corrosion. There's going to be fouling. I know that if I deliver my piece of equipment today to meet 100% of the BTU requirement, that a week from now, as things degrade, well, it's not going to be able to perform adequately. So I'm going to design basically a safety factor into the process heating capability. And in order to do that, I'm going to increase the size so that by doing that, as it degrades over time and the U value drops, at a year time or 2 years time, some point in time that can be planned out, then the customer will be able to pull that tube bundle out and clean it and then be able to start fresh again. But starting from 0.0 from right now, because it's got a very, very high an A value, then that means that process heater has a lot more heating capability than we need. So in order to compensate, that heat exchanger is going to throttle its LMTD, throttle its BTU delivery, and reduce the pressure to the steam, and end up potentially with a negative differential scenario. So got an example here. I'm going to go through this just very, very quickly just to save on some time here. So this is what I would consider a full load condition. So one scenario here where we've got inlet temperature of 100. We're trying to increase temperature out to 240. We've got our steam inlet control valve, fixed outlet pressure of 20, product flow rate of 10,000 pounds an hour, steam flow of 6,200. So looking at all those, we can, back up, look at all those, we can see or estimate a differential pressure, positive differential pressure of 95 psig. So one of the exercises I would take through my class, typically if we've got some more time, is I would have them pick out the TLV steam trap. So in this case, it would actually be this particular model you see right here. So that was the full load scenario. Now we've got a normal load scenario. So process temperatures are the same, but now we've got a slightly reduced flow rate, which corresponds to a slightly lower steam flow rate because we need less BTUs. And we've got less pressure as well. It's going to end up in a lower positive differential pressure. Again, we can still size the steam trap. Now we've got a reduced condition scenario, or a turn down scenario. Our product flow rate drops even further, steam flow rate drops even further. And now we're in a scenario where we've got -9 psig differential pressure. So because that's negative differential, then steam trap is not going to work. So one of the things that TLV offers as, it's actually a tool we developed a while back. It's called a stall chart. This is a way to look at all of these different types of scenarios, and not just your full load, normal load, and reduced load. It's a way to graphically represent everything that's happening from your worst case design load to your worst case low load scenario. And what we're able to do is plot basically all the conditions on a graph, put some lines together, and we're able to see that we have a stall point. And just to briefly explain what's going on here, we've got pressure on the right axis here. We've got our load percent on the bottom x-axis, so you can kind of think that as heat demand. And then corresponding with the y-axis on the right, we've got this y-axis here in the middle. That's the saturated steam temperature corresponding to those pressures. So without going into too much detail, what this is showing is that with a fixed back pressure, we have estimated steam pressure inside the coils from full load at 100%. Pressure is dropping all the way down to 0%. So we can see that right where these lines cross is the stall point. So everything where your red line there is higher than the green line, we have a positive differential pressure. Steam trap's going to work. If that red line is below the green line, then it's a negative differential pressure scenario. So trap won't work. So you could say that, all right, Justin, I'm going to tell you that my process heater never ever operates below this 63, 64% mark. Sure, okay, fine. Steam trap will work, not a problem. But if you're ever below that, steam trap's not going to work, and you're going to have all those suboptimal symptoms. Probably an operator is then going to have to open a drain and discharge condensate to the pad. So that's a problem. And we need to look at a different type of drainage solution than a steam trap alone. To make matters a little more complicated, we consider the oversurfacing that I'd mentioned earlier. Then that can change the stall point. That actually shifts it higher. So you can see in this scenario here that that 100% of the heat demands that were already installed, meaning that no matter what this process heater is doing, that from day one, this customer is going to have problems with operating this heater. They're going to have problems potentially with water hammer, with controlling temperature, with getting off-spec products, with gasket leaks, with all these issues that you guys are thinking of. And it has nothing to do with the heat exchanger. It has nothing to do with the trap itself. It's just a mismatch on the drainage solution with that process and what that process heater is doing.
Hey, Justin, let me stop you right here. We got another poll. What do you say, Justin? What do you think is the most common thing that you see that results in this stall?
The most common one is low process temperatures.
Okay.
It's almost a guarantee if we talk about like a hot water heater, just because, hot water, unless it's processed hot water, is usually very low temperature, meaning below it's 200 Fahrenheit.
And what's it? Go ahead.
The other one is where you have light oils. Oftentimes those have low heating set points, whether it's a tank heater or a process heater. Oftentimes those are low temperature. So it really depends, but that's usually the biggest flag. I can usually, if I have a conversation with an operator or the customer or an engineer, I can say, hey, what are the process requirements? What is the inlet temperature and your set outlet temperature for this? And without looking at anything else, I can, pretty accurately usually say that, yes, that's more than likely going to stall just because it's a very low temperature.
Would you say that the oversurfacing is maybe one of the most detrimental problems? Just because, I mean, if you're oversurfaced, you have to actually change out your equipment, right? So is that probably the most extreme problem that's hard to remedy?
So it's a double-edged sword. So the oversurfacing there is to, in effect, protect the ability of that process heater to deliver the amount of BTUs that's required, even after things like fouling have occurred or other degradation of the U value. So that oversurfacing is required, and that's really dependent on the type of process. So if it's, let's say, an air heater, well, then air is not really going to foul on the process side. And so typically you'll have very, very low oversurfacing for those types of heaters. But if it's something like, let's say, a crude oil heater or some other type of heavy hydrocarbon that has a tendency to burn or, cake on, then usually we see those types of heaters have a very high oversurfacing area. And that's to protect that piece of equipment, to make sure that, it can continue delivering the BTUs that are required even after it fouls. The problem with it is that extra oversurfacing, then it's beefing up the heater to give it more BTU capability than we need. And so to counteract that, the control valve has to throttle down and deliver a lower pressure. So that's not a problem in and of itself, but it ends up becoming a mismatch with the process heater itself and the drainage solution. So whereas, not considering, that type of scenario, you would think that, okay, steam trap should be just fine. I've got plenty of pressure. But you weren't considering this, very, very high oversurfacing. Well, now all of a sudden, control valve has to throttle down more than what you were originally anticipating. And then that leads, hypothetically to a negative differential scenario.
Okay. Yeah, great. All right. I think everybody's responding to the poll, so I think we can keep going.
So big question is, all right, I hear about this stall. I hear it's a problem. I recognize all the suboptimal symptoms that you've said. What can I do to overcome that? Well, there are some easy options and there's some more complex options. So the easy option is using a steam trap only and allowing gravity to work in our favor. So here's our process heater again with our inlet control valve and our steam trap. What we need to do is eliminate the back pressure. So if you didn't see that, we've got condensate that is discharging overhead to a pressurized return. If we can discharge that to sewer, well then great. That might help to overcome stall. Now, of course, that's maybe not an ultimate goal. Maybe, depending on the state that you're in or your local jurisdiction, you might not be able to do that. Or if it's an indoor facility that doesn't have a drain nearby, then you might not be able to drain condensate to the sewer. And you might be stuck with problems. But if this is something that you can do, well, then this is an option. In addition to that, doing some slight piping modifications. So going to basically drop that trap as far down as possible to increase the fill height. So what that does is allows a volume where condensate can back up, not necessarily into the heater itself, but in the upstream piping, remembering that we've got, for every 2 feet, we've got 1 PSI hydraulic head. So if we've got, let's say, 4 feet right here, well, that's 2 PSI upstream of the trap draining to atmosphere. That's a 2 PSI positive differential pressure. It's not much, but that's something that we can work with, and we can size a trap for
that. Justin, can you speak to why you can't lift the trap up to decrease your back pressure?
Lift the trap up like this?
Like if you had the header up above and the trap, you raised the trap up to the header height. What problem would that? I'm kind of leading you, but what problem does that cause?
Gotcha. Yep. So great question. So yeah, hypothetically, if we were to raise this trap higher, then that reduces the hydraulic head due to lift on the downstream side of the trap. Now that sounds great and all, assuming you've got enough volume here to work with. So if we begin backing up condensate due to some stall scenario, well then what's the scenario? What's causing that, right? Is that high back pressure or is it low steam pressure? So it could be a combination of both. That lifting up this trap may help, but usually by doing that, you're only mitigating or eliminating, a few feet of piping, which would only decrease your back pressure by a couple PSI. So probably I would guess in most cases that wouldn't really help, but it's definitely something that should be considered.
Yeah, thanks. And I was upstream of the trap, it's all the same pressure, right? So it has to flow to the trap through gravity, regardless of what's happening downstream. So you can't put the trap above the minimum water level of the heat exchanger, or you're creating a stall condition, right? So
right. Great point that you absolutely want to have the trap below the outlet of the heater so you can gravity drain from the heater through the trap. If it's above that, well then the pressure in the piping here is going to be the same as the pressure in your heater, and it's like a manometer. It would literally have to back up condensate in the heater in order to be able to drain through the trap. Now, this scenario is also assuming that you've got positive pressure inside the heater. A lot of times you might not have positive pressure. So in doing that lifting up the trap wouldn't help at all. You would actually have to drop it down, discharge to sewer, and then on top of all that, install a vacuum breaker. So in this scenario, and this is a very common scenario, where your process temperatures are very, very low and the the steam pressure required to deliver the amount of BTUs that are needed is low, well, then you would, by eliminating the back pressure, increasing the fill height, the next step you would want to do is install a vacuum breaker. So that basically allows, when vacuum begins to form, it allows air to ingress into the system. It equalizes the system so that now we're at atmospheric condition inside the heater, and then allows that liquid level here to be able to give head on top of the trap and allow that to drain. So even under the lowest BTU demand scenario, then we still have, let's say, in kind of the scenario I was giving you for 2 psi positive differential pressure across the trap. So caveat here is that the trap that's selected, absolutely need to make sure that's got an integral air vent, and it can operate under normal steam pressure conditions. So what's probably going to happen is that the control valve will see that, the process control is going to see that air is in the system. The process temperature will slowly begin to cool down a little bit, and then the control valve will begin to open up a little bit and try to force that air out. That air can't get out, well, then that effectively vapor locks the system, and now we've got air stuck here, all the while condensate still being produced by the process heater, but now it's backing up again into the heat exchanger, and so that becomes problematic. So really need to have all four of those things, eliminate back pressure, increase fill height, install a vacuum breaker, and make sure your trap has an air vent in order to mitigate a stall situation using a trap alone. But as I alluded, if you must return condensate, well, then increasing the fill height's not going to work. Adding a vacuum breaker is not. You're going to have stall still. But there's a solution. So that solution is a mechanical pump trap, or in TLV lingo, it is a power trap, or you might have heard of a secondary pressure drainage device. So there's our trap. This is our power trap. Now, this might look very complex, but it's quite simple. So I'm going to try to focus in on all the pertinent parts here and go through this step by step of what happens. So our process heater is generating condensate. That's going to gravity drain down to a reservoir, down through some extra piping, begin filling up our power trap device right there. During startup, or let's say there's air, we're going to be displacing vapors, and the air is going to be pushed out the air vent. If it's in a positive differential pressure scenario, then this will act just like a steam trap. And the moment that we have negative differential pressure, well, then condensate begins to back up and we're in trouble. Wait, no, we're not in trouble. There's a device inside this power trap that it's basically a high level limit that mechanically senses that when it gets to that certain limit, it's going to engage 2 sets of valves. It's going to open up a valve here, allowing high pressure motive source, in this case steam, to come in. This would be steam sourced upstream of our modulating control valve. And it's going to close this equalizing line here. So in doing that, it's going to pressurize that pump body and begin pushing out that condensate. Now, all the while, we have condensate that's still coming from the process heater. So we have a check valve here, so our steam's not back feeding into our reservoir and back to our process heater. But because that check valve is closed, then we have a liquid volume that's going to build up. Now part of the reason why this reservoir is here is to more or less act as a buffer so that we can back up condensate inside the reservoir and not back it up inside the process heater. As soon as all the condensate's pumped out, that internal mechanism is going to re-engage that valve assembly. It's going to allow that high pressure steam to exhaust, and it's going to equalize with the reservoir and equalize with the heat exchanger itself and begin allowing condensate to gravity drain back into the pump. That cycle is going to go over and over and over again. So taking a closer look inside, got a check valve, outlet check valve. This is basically a lever float type device where we've got a linkage here. It's tied to a double-seated trap where if we have positive differential pressure, then this float's going to lift up and it's going to push down this plunger, effectively exposing more area for condensate to pass through. And it's going to act just like a steam trap. And we have negative differential pressure. Condensate's going to continue to fill because no matter how much this trap opens up, we don't have positive pressure. Condensate's not flowing. It's going to continue to back up as we see right now. We get to a high limit here. It's going to engage a snap action mechanism. And you'll see that this valve for the exhaust closes. This valve for the motive line opens and fills the pump body and begins pressurizing pump body to push it out. As soon as it gets down to the low limit here, it's going to re-engage these, open up the exhaust, close the motive valve, and exhaust that back to the rest of the system. So a few important points here. Elevations. So we've got our reservoir elevation. This is, we've talked about hydraulic head. This is a way to help increase the nominal pump capacity. So if we're able to increase this elevation, we're effectively allowing more condensate to build up upstream of the check valve. And because this check valve has a cracking pressure, it's going to limit the amount of flow. So if we can increase the head pressure upstream of the check valve, that will allow more condensate to flow through that check valve. Or we've got to make sure we balance that with the equipment elevation, because Chase very astutely mentioned earlier that we need to make sure we're gravity draining from the heat exchanger through, in that example, to a trap, but in this case to the reservoir. We make sure we're balancing the elevation of this reservoir with the elevation of the outlet of the heater to make sure that we're not having to lift up to the reservoir. If we do end up having to lift up, well then we're back in the same situation where we're flooding the heat exchanger and getting all the same problems that we're familiar with stall. So want to make sure that we've got gravity drainage working in our favor and avoiding any piping loops. So big critical point here is the equalization line, making sure that's properly sized, properly piped from the power trap to the receiver, as well as the equalization line from the receiver to the equipment itself. The whole point is to make sure that the pressure inside the heater is the same as the pressure in our reservoir and is the same as the pressure inside the power trap. If that scenario happens, then condensate can gravity drain down. If there's a scenario where, let's say, either of these begin to creep up in pressure because there's a restriction in the line or a blockage, or it's tied to an incorrect location, well then basically we can get to a scenario where this begins to pressurize, and now we're back to a negative differential scenario where we have a lower pressure here and a higher pressure here. Condensate cannot gravity drain, and this system either may malfunction or has a reduction in capacity, all of which are going to cause problems. So critical point here is that we've got, at least for shell and tube heaters, there's a specific location we want to make sure we're balancing to. It's a little easier when you've got shell and tube heater with steams on the shell side. But point here that I'm really wanting to make is that TLV, if you ever are interested in utilizing a power trap system, or you're out in the field and you see another type of mechanical pump system, just understand that it requires balancing, and the balance point on the heater, whether it's a shell and tube, plate and frame, fin tube, or anything else, it needs to be balanced to lowest pressure vapor space. And sometimes that might actually be the condensate outlet piping. And if so, it's just a lot of considerations for designing this piece of equipment and what those elevations and the sizing of various things look like. So getting into, well, how do we size this? What does this look like? TLV has developed a form. I know everybody just absolutely loves forms. TLV loves forms, but it's a way for us to collect all the critical information so that we can size the power trap system for you. So got all the green areas filled in. And then what we're going to do is we're going to create that stall chart for you. We're going to show what our estimated stall point is. And then based on that analysis, we're going to make a recommendation. Say, hey, this piece of equipment, appears to be in stall, and here's all the operating conditions you gave us. Here's our recommendations with a nice little sketch. Here's other product recommendations and some really important notes that we think you need to pay attention to. So, a lot of different unique geometries out there with available piping space, different scenarios where you might have differing vessel sizes, maybe 1 pump, 2 pump, 3 pumps. What does that look like? So we're more than happy to work with our customers and helping to design these, but we really prefer if you allow TLV to build that for you. More or less, we'll build a turnkey system like this, where it's minimal customer in hookups, and we can build a single system, a twin system, triple system, or we get into very complex, custom, unique type packages like you see here, in order to accommodate a range of different needs for customers. So that is the conclusion of my presentation. If you have any questions, I'm not sure if my contact information is anywhere, but please feel free to reach out directly to me, or you can contact TLV North America at 1-800-TLV-TRAP, or our consulting, engineering, and services team at ces@tlvengineering.com.
Oh, I pulled the trigger a little bit early on taking over the screen there, but
no problem. It's perfect timing, Chase.
Thank you, everybody, for joining. We're going to hang out for a few minutes. I know we're coming right up on 12. So, anybody that needs to drop off, you've completed the presentation, and